Episode 33 of the World of FPGA Podcast. Signals have to get into the FPGA and out of the FPGA. Here we need input and output pins, and here we have a closer look. Welcome to the World of FPGA Podcast. I'm your host, David Kirchner, and I will lead you through the world of FPGA. And now, let's begin. Today, we take a closer look at FPGA IOs. Well, with our ears, because it's a podcast. And we go from the outside backwards into the FPGA. So let's start at the I/O pad. First, the I/O pad with all the ESD and overvoltage protection stuff is our starting point. Here, for example, the bond wire, or in flip chip, the direct connection to the outside. Here we have the connection to the real world. And only here have we a real bidirectional connection. This is the only point where we have a bidirectional connection. And after this point, it is splitted into an input path and an output path. Normally, all signals inside an FPGA has only one direction, from a source to a sink. But the I/O pads, and that's the name, it's an input and output pad, they have the possibility to be bidirectional. So to send a signal out and at the same time to read it in and using it for the signal stuff. Okay, so at this point we have a splitted path, an input path with different options and an output path. The input path has different options like LVDS or Schmidt trigger or things like that. And we have also different reference voltages that can be used to match the incoming signal. This is often used for special signal standards for high speed, but every input must have a kind of reference voltage, because we have to compare the incoming voltage. It's an analog world at the outside. Or if we have digital signals, it's also an analog world. And at that point, we need to compare the incoming voltage with a reference to get a 1 or a 0. And we have an output path. The output path has different driver strength and slew rate and so on for different output standards. And most output driver can also have a 3-state mode. So we can control if the output is working or is it floating to use it as an input. Important is this functionality, for example, of course, for bidirectional signals like A2C data path. And this is needed because exactly here we get from the digital world with ones and zeros to the analog world and the outside of the FPGA, as I said this before, for the input stage. When we go on, we will come to some kind of logic block. Often we have very close to the I/O blocks or the I/O pads some flip-flops and some shift registers. These flip-flops can often be used for example, double data rate functionality, but it is depending on the manufacturer, which features are included or which features are not included. And there can also be other features like delay blocks. So a signal can be fine-grained delayed in picoseconds, or I don't know if femtoseconds, but so there are femtoseconds, but I don't know if any FPGA can delay it by femtoseconds. I guess it's more the picoseconds. So you can, if you have multiple input signals, you can align them, or you can compensate the incoming copper trace length within the FPGA if you use some kind of delay block. But of course, not every I/O has that, and not every manufacturer has that, and not every, and so on and so on. It depends, like a lot of other things also. And some of the FPGAs have some kind of serializer, deserializer. So signal can be serialized or deserialized, always with the high-speed side, so the serial side, to the outer world, just to achieve higher data rates or to use only a few wires for your connection if you have a lot of I/O signals you want to connect to your FPGA. In many FPGAs, these logic blocks have their own local clock network. But about clock networks I will talk in a later episode. Yeah, and signals from the logic block will, from and to the logic block, will get then to the other logic inside the FPGA. So this is the point where you get into the rest of the logic inside an FPGA. Maybe you will go to the next FIFO, or you go into calculations or in the state machines or things like that. So from here, we are getting into the rest standard world of the FPGA. When talking about I/Os, I would also like to have some words about I/O standards. So let's talk a little bit about I/O standards. The I/O standards in our FPGAs are defining the voltage levels and also some signaling characteristics. It is needed that we can, this is needed that we can connect our FPGA to other devices. And it is very important to choose the correct I/O standard to ensure that we have the correct signal integrity and that our FPGA can operate correctly with the external devices or external FPGA or whatever we want to connect to our system. And there are mostly two types of I/O standards. We have the single-ended I/O standards and we have the differential I/O standards. And in the single-ended standards, we have, that is the most common and is most simple to implement this into an FPGA if you look from the chip design side. So they're using only one wire to transmit a voltage. And this is compared, as I said before, with a reference, and it has a common ground. That's a good idea if you have only a few I/O pins. It's a bad idea if you have some EMC things like immunity or immunity problems. Then single-ended is not the best choose. So at standards, we have the really standard. It's LV CMOS. It's a low voltage CMOS input. CMOS, it's the complementary metal oxide semiconductor. And it's very widely used standards for general purpose I/Os. It's used for different voltage levels from 1.2 volts up to 3.3 volts. And in between that, we have normally the 1.8 and 2.5 volts. And the voltage is normally chosen by the I/O voltage of the I/O bank. And also the voltage to compare for zeros and ones is often derived from the I/O voltage supply connection. A very old standard is LVTTL, so low voltage transistor logic standard. It's quite old and normally we are just using LV-CMOS for our designs. If you're going to higher speeds, you want to have some more improvement and more things for termination, and then you can use, for example, HSTL, so high-speed transceiver logic. It's designed for high-speed memory interfaces, for example, SDRAM, DDR SDRAM. And it's using its own reference voltage just for fast switching, and also important to improve noise immunity. Another high-speed standard is SSTL. It's a stub series terminated logic, and it's also used just for high-speed memory interfaces, sometimes for DDR SDRAM. And it's required a special termination scheme to get the correct signal integrity. The other side, we have the differential standards. These standards have two complementary signals to transmit data or to receive data, and it is so it's much better than single-ended in the case of noise immunity, and it is always the best choose for higher data rates over a long distance. So think about, for example, Ethernet. Ethernet has, so if you have this original 100 megabit Ethernet, you have two pairs, a transmit pair and a receive pair. And here we are transmitting over two pairs, a differential signal over, well, I guess the standard says 110 meters. Now, that's quite a long distance. And also gigabit or 10 gigabit is always running over a long copper wire. Or think about DSL or things like that. It's working with differential signals. At the FPGA side, we have three differential signal standards. The first and most common is LVDS, low voltage differential signaling. It's very popular for high-speed differential standard in various applications, in video interfaces, in high-speed data acquisition, and so on. So LVDS is normally your standard if you want to connect some high-speed components together. And some FPGAs can also doing all the termination stuff inside their I/O blocks. That's interesting if you want to save space on your PCB and not to put a termination resistor near to your FPGA I/Os. The next standard is TMDS, Transmission Minimized Differential Signaling. It's not exactly the same as LVDS, but it has a lot to do with LVDS, and it is commonly used for video interfaces like DVI or HDMI. And we have also CML, so current mode logic. This is used for very high-speed serial communication, and we found it often if we have ZERDES applications. So if we want to transmit very high-speed signals over one pair, then we are using a current mode logic. Well, the main considerations for I/O standards are, for example, voltage compatibility. So the primary consideration is that the I/O standard of the FPGA is matching the interface of the device you want to connect to. If you have incompatible voltage levels, well, it can be that the device or the FPGA is damaged, or that ones and zeros are not correctly detected. The next is signal integrity. That's important for high-speed signals. You always need a proper termination, parallel termination, serial termination, and so on. There are a lot of things you can do. And as I say, sometimes FPGA have an internally digital controlled impedance to help with the correct termination. Next is power consumption. Yes, of course, the I/O standard also has an impact for the overall voltage consumption of your design. If you're using a standard with a high voltage and you want to terminate it and run it at high speed, well, this would consume a lot of power in comparison with, for example, an LVDS signal. The next is I/O banking. So FPGAs, mostly or all of them, I'm not quite sure, but I guess all of them have some groups of I/Os building one I/O block or one I/O bank in your FPGA. And each bank has its own power supply. And that means that if you have two different output standards, they have to use the same voltage, and that's not always possible. So on the input side, often it's possible, but on the output side, well, it could be not so easy. Well, the last thing consideration is data rate and performance. differential I/O standards are suitable for low and for high-speed things. Single-ended is not the best choose for high-speed signals. But well, in the next episode, I will talk a little bit more about I/O standards for higher speed. And I want to give you some examples how you can push your design to get faster for high-speed designs with single-ended standards. If you were in my lecture or my talk at the FPGA conference this year, then you will get you will hear some things you has also heard in the talk. Well, and that's all for today. All information can be found at the world-of-fpga.com/WFP033. If you found this episode helpful, please rate it on Apple Podcasts and share it with your colleagues and friends. That's the end of today's podcast episode. Thank you for listening and for your attention. So I say goodbye here and next time, your David Kirchner.